I'll start by talking about mundane things. I promise, I solemnly swear, and if I make this commitment to you, there will be social pressure, that I will get to the store and diversify our candy offerings soon. I haven't done it yet because I live right in the middle of Squirrel Hill, and that Rite Aid is where I used to get my candy. And so my whole system is destroyed. It's just my whole, yeah. So what if I say it to you, now there's social pressure, and you can ask me, hey, Claire, weren't you going to do that thing? And then I feel obligated. So feel free to ask me about that. Last Wednesday, I talked to you about basically testing model accuracy and some of the challenges there, and particular pitfalls. And so today, nice natural transition, we'll talk about model testing beyond accuracy. Let you laugh at XKCD for a moment. We'll start by talking about curating validation data and input slicing. But actually, before we get there, let's not talk about testing models at all. We're just going to talk about testing, right? All of you have some experience writing some code, so the idea of a test should not be completely foreign. So imagine I've given you this problem. Maybe we're in a class that focuses exclusively on software engineering. I say, look, I have a program that takes next date, called next date. You give it a year, a month, and a day, and I want you to test it for me. So imagine I can write tests that are just assertions over the output, right? So let's have a slight change in our usual modality. We'll have a breakout discussion now, and then hopefully again later, assuming I manage my time appropriately. Let's talk about how many tests do you think you need to be confident that this is correct, and how would you pick them? Okay, that's the conversation. You look like you have a question for me. No, okay, you're just thinking about the question. Okay, so that's what you're going to do. This is your method, your function. I want you to test it. How many tests do you need to be confident that it's correct? No, I didn't give you the code. I just gave you the function signature. Okay, talk about that for a few minutes. Put it in lecture, and then we will discuss it. And if it's like every other time I have given this task for discussion, your answers will vary wildly, and it's going to be great. So go ahead. How many tests?
I think 30.
30? Okay. Who has a different answer? Everyone said 30. I know that's not true. I'm looking at your answers, so I know that's not true. Everyone's rapidly changing it so that it says 30.
We said roughly 10.
Okay.
Because we went and labeled with fingers up.
Okay.
And a strange test that we considered was before the AD.
Okay, so yeah, boundaries of years. Okay. 10-ish. 10-ish, largely driven by corner cases, maybe? Okay. I hear a bit of a theme, which is that we are talking about edge cases here.
So we're thinking maybe toward special
Classroom mic's not picking up like it's supposed to be, which I don't know if it's supposed to be, but it's not. So
February and leap years. February.
Leap years in February, always a problem.
And also February without leap years.
Oh, also February without leap years. Well, February is weird in general. So I'm looking over, I see a bunch of answers, right? I see, I see the range. I see 4 as a lower bound. I also see, 20 unique edge cases and then 30 general cases, which smells like a fair bit. 5 to 10, I think, is maybe the most common answer as a ballpark. But I also see a pretty consistent theme here of, you're thinking about what are the common cases versus what are the corner cases. My curiosity is, if you were asked this question, okay, I could see how if you're in a software engineering class, right, and we're talking about test coverage and whatever, maybe you say 30. But if you're actually testing this, I'm willing to bet money, a thing I don't do, that you'd all be happy at about 5, right? Because you wouldn't actually write 30 test cases for next date. But I do think the thinking of, okay, what are the kind of corner cases? Where are the places that people are likely to screw up, right? Because just, I think if this one passes, like, I don't think we need to check all the other normal edge cases, right? Like, I don't think we need to check the other normal edge cases. And maybe there are other edge cases we'd want to check here, things like related to, I don't know, invalid months, right? What if I gave it 15? Or what if I gave it, I don't know, negative numbers, right? Those are some edge cases that I don't think I heard or saw anyone say. But the point is we want to think a little bit about boundary values and so on. Okay, so that is kind of standard testing. I have, again, lost my controls. Here we go. But some things you may be noticing about your answers is that you're focusing really on the high-level specification here, right? On concepts from the domain. You're talking about things like leap days and month lengths, right? You're thinking about things we know about how time's supposed to work. And nobody, I think, so I didn't see this in Slack, proposed to randomly sample from all days, right? This is a strategy in testing to do random sampling. Not one that we'll be talking about much because it doesn't apply to modeling. But I think in terms of this kind of task, I think it makes sense that we wouldn't do that, right? That's a kind of a specific, often security-focused kind of strategy. So classic, since it is a software engineering class, I have to give you kind of the classic software test case design definitions. One way these are often decomposed when we're talking about what kinds of tests there are is opportunistic or exploratory testing, the kinds of things we do when we're just kind of prototyping something, right? A couple, don't think about it too hard. Then there's a class of techniques we often refer to as specification-based testing or black box. It's called black box because the idea is you're not supposed to be looking at the implementation, right? You're just thinking at a high level, what is this code supposed to do? That's the thing we did on the previous slide. And the kinds of things you were talking about, right? Boundary value analysis, you were thinking about weirdness corner cases, right? Advancing from February 29th to March 1st. And equivalence classes, right? There's a reason I think nobody said test every day in a year because, if you can handle one normal day, you can probably handle all the normal days. So a combination of that and sort of edge case testing is a little bit more principled, thinking about the specification. Other kind of classic techniques here that we won't really be talking about are combinatorial and random testing. We tend to contrast that with structural testing, sometimes also called white box testing. Called white box because the idea is we're deriving test cases by looking at the code and trying to cover various paths. So if you have used anything in your IDE that gives you coverage, right, branch coverage, line coverage, if you were writing tests to increase those numbers, you'd be doing white box testing because you're trying to cover certain kinds of interesting paths through the program. This lateral sort of structural testing doesn't often apply really in the machine learning context, right? Because you can't really cover like the neurons. Or I mean, you can. People like talk about this, but that's not really our focus. I think those techniques are not as instructive. In general, test execution is automated, but can also be manual, right? We can automatically generate from specifications or code in the traditional sense. I think that this division is a little needlessly academic, right? Like nobody actually sits down without looking at their code, and like nobody does that. But it's good to know the principles. Now you just did this, right? Boundary value testing where you're analyzing the specification. And the idea here is that errors often occur at the boundaries of a variable value. And this is what informed like a bunch of your suggestions when testing next date, right? You were thinking about weird things that happen when it's February and a leap year and so on. You also thought about this kind of equivalence class things, right? That many of values will behave similarly, but some groups are meaningfully different. And so maybe we want to check on the like 30 versus 31 months, but we don't need to check every month with 30 days and so on. So I don't think we need to do this again because I think you get it. Instead, let's take a step and talk about what we're actually talking about. So how do we kind of port some of these ideas for validation data for model quality, right? What are the ways that we can port some of these ways of thinking about testing to evaluating model quality, right? We're not just looking at accuracy anymore, right? Accuracy on a data set. I'm just saying we want to test quality a little bit more broadly. And I think a key idea worth realizing here is that, like, not all inputs are equal, right? There are different classes of cases for AI-oriented software in the same way that there are different classes of cases for date-time code, right? So here, if we're testing an Alexa, right, some things are very frequent. Call mom. What's the weather, right? And some things are much less frequent. And so as you think about different input classes for a different problem, right, some are very frequent and some aren't. Meanwhile, like, there are also edge cases, right? In the same way there are in classic software. Like, these are largely taken from self-driving car data where the edge cases can be very, very rare, but also extremely important. And so we don't want to treat these equally in planning our testing strategy, right? When you think about how good or bad, right, random mistakes can be, like random mistakes versus rare but biased, or rare and very bad mistakes, right? You need to think about kind of, again, how bad the thing is, right? How bad the thing is you want to avoid. And we touched on this a little bit when we were talking about false positives versus false negatives and which is worse in your application. And similarly, this is very domain specific, right? Like, there are certain kinds of mistakes that are rare but especially problematic. So the question is, right, how do you identify important inputs and figure out how to test them? The kind of key idea here, right, is you want to be curating your validation data for specific problems and subpopulations. And so things like important or very common inputs, things like call mom, we probably expect very high accuracy. And for these kinds of input classes, it's probably the closest sort of emotional equivalent to what we call unit testing, right? You want to test kind of like the happy path, and it should work super well on those kinds of samples. Between different key subpopulations, sliced in various ways, at least for an Alexa, right, we would expect comparable accuracy. So different people who have different accents in speaking a language, we hope it would be equally roughly accurate. We might, though, accept in more challenging categories, right, some lower accuracy for particularly unusual phrases. So in terms of figuring out what are the classes of data, you need to think about the domain. And the kinds of behavior you expect on those classes of data, right, depends on the importance of that class, right, or the distinctions between the classes. These are all derived from requirements, right? It's like specification-based testing, the kind we just did on datetime. So how do we get that? Standard approach to doing this is what we call partitioning, right? So guide testing by identifying important subgroups of the domain and then analyzing accuracy there. This is often, for fairness, things like making sure that the model performs equally well for people based on gender or country of origin. But it can also be derived from business requirements, right? Or the cost of mistakes. This can help you identify problems, of course, and then plan mitigations. So there are so many examples here. This is from a paper. Where does my model underperform? A human evaluation of slice discovery algorithms. This idea of finding data to help you understand performance differences between subpopulations is related to an idea called slicing, where you take your input data and you cut it into pieces based on the slice of the subpopulation that you care about. There are lots of papers here. So for example, this system, the idea is you have a hypothesis that the model underperforms at detecting cats in photos where they're curled up adorably to sleep. And so then you'd want to slice your input data to find all the adorably curled up cats and evaluate accuracy there as compared to other subpopulations. There are a number of tools here. This one's called Zeno, right? The idea is we're comparing accuracy on different subpopulations. And this is not just the realm of academic tool builders or HCI people, right? This is getting a little older when they were talking about this, but the system at Apple called Overton is effectively enabling this at scale, right? The idea is that they want to focus their engineers on creating training and validation. So they have this infrastructure to help engineers slice telemetry data and identify underperforming subpopulations. And then they can focus on creating better training data, right? Use semi-supervised learning and so on. So I actually won't largely be talking about cancer prognosis, but that's the one we were talking about last week. So what are some examples? How could we slice evaluation data for cancer prognosis? Just to get you thinking. Don't all talk at once. It's weird when you do that. Yeah.
Age groups.
Age groups. We want it to work well on different age groups, right?
Like stages of cancer.
Stages of cancer. That's a good one.
Types of cancer.
Types of cancer.
Their medical history.
Medical history. I'll give you a free one. Gender, right? There are lots of different categories here, subpopulations. And here we'd be using these slices to make sure that, accuracy was acceptable, basically in terms of how bad the incorrectness would be. Right? Maybe we want it to be super accurate for later, more dangerous stages of cancer and so on. So most of the examples are times when we have little thought experiments. I actually want to talk about a different kind of use case, namely Excel AI. Right? Microsoft is shoving a lot of AI into Excel. For good, that was a value-neutral statement. It was not a judgment. But you all kind of were like, yeah, they are. So let's think about that when we're talking about most of our examples today. How should we slice evaluation data for that kind of tool? Right? It's going to be doing things like helping you write complicated spreadsheets, analyze your data. Sort it. So give me a little more detail.
So you sort according to the parameters that, for example, gender, making sure you have full distribution of gender
In Excel?
evaluation data. You can file your lines of.
So, no, I'm just keep talking. It's fine. I want to make sure I understand your suggestion.
Yeah, like create a subsheet within your sheet.
Okay, yeah.
A certain count of males or a certain count.
Okay, sure. So maybe you have different kinds of data that we're going to be doing simple operations on, and we want to make sure that they work well. You could think about, here Excel has so many features, right, that thinking about different subcategories may be a little tricky. But maybe there's things like, easy formulas to fill in. Maybe there are harder formulas to fill in. Maybe there are complicated data transformations, pivot tables, a thing nobody can do, right? Maybe there's some good categories of examples there. So I just want to get you thinking a little bit about a more complicated AI sort of agentic system. And so we'll come back to that over time. Okay? So one strategy here, or set of strategies here, is something we call behavioral testing for capabilities. It's nice in that, a lot of these ideas from the model, the ML kind of community, have corresponding concepts in software engineering, even if the language that the different researchers use are different. This kind of involves thinking about a model and what it should do in sort of a unit testing kind of way by breaking it down into slices of functionality, sort of like what we've been talking about. So here, the idea is like we should basically say, what should this model be able to do, right? You define capabilities that the model should grasp, and then create targeted test cases for those capabilities, right? So here, if we're trying to do sentiment analysis, right, that's the example from the paper. They looked at a lot of NLP tasks. It should be able to do whatever the NLP task is when you replace words with synonyms, right? If I say a sentence is positive, it should still be positive if I replace every word in there with synonyms. We should, if I'm trying to do sentiment analysis, if I insert a negation in a semantically meaningful place, it should flip its assessment, right? These are capabilities of a model that does sentiment analysis. So this is, again, use case specific. And analyzing common mistakes, right? Using existing knowledge, observing humans, right? Deriving from the requirements, or even causal discovery from observational data can help you identify certain capabilities. So this might help a little bit with us thinking about the Excel example, right? So here's Copilot saying, here's a pivot chart that shows an insight about your data, right? You can ask questions. So what are some capabilities of Excel AI? Maybe if we're looking at this, right, we have data that's country, customer, product, discount, units sold, manufacturing price, sales price, gross sale. What should Copilot do well? What are things it should do?
Forecast the sales.
I'm sorry?
Forecast the sales based on the time.
Right, so what is a capability there? So if, how would we put that, right? So in terms of natural language processing, right, if a sentence is replaced with all synonyms, it should give us the same answer. So here,
If the project is different, but the sales are still the same. Like,
Yeah, so maybe if the sales are still the same, but everything else is different, like the chart should be the same, right? Like if key data, if all the data that's irrelevant to this changes, but the important data stays the same, then the chart should stay the same, right? There's a capability. If it's doing transformations of certain kinds, right, it should do those correctly for certain classes of data. So capabilities are a pretty common paradigm, even if they're not always called that, in testing for LLM systems or agentic systems. If you think about the massive multitask language understanding benchmark or human eval, right, the first is a set of multiple choice questions across a number of subjects. And there's a way you can think about that if you're slicing by subject as slicing by capability, right? And you can compare accuracy across different groups. They're both kind of operationalizing what should this model be able to do. If we just looked at accuracy across 16,000 multiple choice questions and didn't think about capabilities, right? If we just took the techniques we talked about last week and didn't think about subgroup performance, then you might end up collapsing important distinctions. Maybe a model is really super good at US history, but trash at law. And if the model was supposed to be good at everything, you wouldn't see that. Right? So thinking about these kinds of data sets in terms of covering a set of capabilities and slicing that way can help you be more nuanced in your evaluation. Human eval, as a person who works on this kind of thing, I have a lot of opinions about human eval, but human eval is a set of handwritten Python programming problems expressed as a function signature and a doc string that explains what the produced code is supposed to do. It's supposed to be used to evaluate basically code generation or code synthesis models. And you can slice them basically by different problem types, right? Different programming kinds of things that they put in there, right? There's mathematical things, there's string manipulation, and so on. So in both cases, right, what these models are doing is operationalizing and slicing what we think these models should be capable of. And they both entail curation decisions, right? Somebody decided these are the problems that belong in here. So if I can distinguish this versus specifications and also slicing, right? Capabilities are partial specifications of expected behavior. You don't expect them to always hold necessarily, but you're like, hey, it should do pretty well on this kind of task. We don't expect them to always hold because no model is ever perfect, right? And some capabilities correspond to slices of test data, and for others, we may sometimes need to create new data because we don't have enough of them. So some of those slicing tools can help you generate data sets for capability-based testing, but sometimes they can't. And there are a bunch of different ways that this can be done. Depending on the domain, test data can be generated using domain-specific generators. So if you think about the NLP example, right? If I say, look, if I negate a sentiment by inserting a negative word, then the judgment of the sentiment analysis should flip. I can generate lots of test data for that, right? I can take a sentence and then negate it using templates. That's what that example is showing. You can also mutate existing inputs. The synonym example, you can take your existing data and just replace a bunch of words with synonyms, keeping the label. You could test robustness against noise and distraction by just throwing random URLs into text, right? Just make sure that it's mostly performing comparatively in that context. Robustness, for example, to spelling errors, too, right? These are things you can do with existing data. These examples are taken from tweets, presumably. Some things, crowdsourcing is better, especially in like NLP, for example, right? Testing sarcasm. That's a hard one to generate because we're not great at it yet. And slicing existing test data, right? You can also just look for negation and sentiment analysis by finding sentences containing not. This is also much of what I was talking about with Overton, right? Where they're slicing telemetry data to find capabilities. Increasingly these days, and we'll come back to some of this, is to synthesize data directly using LLMs. This can give you at least pseudo-labeled data for certain tasks. at least for capabilities that large models are known to have. This is also referred to as distillation, because what you're doing is distilling the knowledge that GPT, for example, might have into specific data related to some capability that we expect them to have. All right, so here's an example of a prompt that might do that. We'll get back to the risks of LLMs for this, not risks, like this is not a terrible idea, but there are definitely trade-offs, and we'll get back to that. So augmentation, there's a fair bit of debate here about like why augmentation is good, or how to test things, make sure that things are generalizing beyond the training distribution. If you're just evaluating on data and not augmenting it, right, it can be difficult to disambiguate from models that are taking shortcuts to those that are actually generalizing properly. And some models naturally generalize better to other distributions that aren't used in training. So, for example, if we go back to cancer prognosis, right, one of the examples of label leakage I was talking about was that some systems will end up queuing on, for example, the hospital or the location data embedded in an image, right? And so predicting whether your model can generalize beyond what it was trained on, you know, is very difficult if you're just looking at one set that's within a particular distribution, which is why augmentation can be helpful. And a sort of general hypothesis here is that capabilities can help, right? Because they are partial specifications that go beyond the training data, right? You're drawing them from the domain, not from the training data distribution. You're saying this is what it should do. And it's encoding domain knowledge of the problem independently from the trained model. So it can help you curate capability-specific test data and can help distinguish models that use intended abstractions and ideally generalize better. So it's a good thing to do, to derive tests from domain. That's why we started by doing it. In general, another thing on terminology, right? Test data curation is a very popular topic for testing ML. There is very little consistent terminology here, both within the field and as compared to software engineering. Many of the concepts from SE translate, but the names aren't adopted, and there's like explicit like name clash, right? Apparently the ML people are using stress testing for testing capabilities, which as a like old school software engineer makes me crazy because stress testing means something, and it's not that at all. Like it's not that at all. And it's fine, like I'm not mad, I'm just like, but it's basically robustness to performance, it's robustness to overload, right? You stress test the system by giving it more volume of requests than you could reasonably expect it in a normal day to get and make sure it doesn't like crash, right? Like that's stress testing. So capability testing, anyway. Okay. So beware. But a lot of actually, we're talking about testing, a lot of it's actually drawing on the concepts from software that do translate, they don't necessarily use the same words. Okay, so a lot of this is me saying, hey, you need to generate more data. We need to test more, generate more data. This is hard to do because you need to know what the answer is for data to know if the thing is correct. This is also a problem in regular software, right? It is often very easy to generate lots of input data for a program and then run the program on it. The question is, did the program do the right thing when you ran it on that data? So for next date, for example, it's super easy to generate realistic input. How do we know whether the answer was correct? And so this is a very like similar issue, right? Like for models, right, we can generate random images, presumably, but how do you get the labels? It's called the Oracle problem. How do we know the expected value of a test? There are a bunch of options. One of them is you can generate a bunch, then you have to do it by hand. That's kind of a cop-out as far as answers go. This one is slightly less of a cop-out. If you assume that you have a reference implementation, which sometimes you do, right? Not always. Then you can compare to that. This is more common in software than in models, obviously, because oftentimes, for example, you're maybe trying to optimize a library, and then maybe you have a slow version. Like you can compare a very optimal sort to bubble sort, right? It's much less common in, we don't usually have a reference implementation for ML problems. Like even if you have alternative models, the problem is that they're always wrong. You might be, there are particular use cases I can imagine where you're trying to train like a much, much smaller model that's a lot faster, and you have a super robust, like super expensive model, but it's not as common. Here's the thing that does not work. So in software, a lot of times we get around this by saying, look, we have a bunch of implicit specifications. We know that software should never crash. We know that it shouldn't run forever, right? We know it shouldn't hang. And so when you do things like fuzz testing, where you're throwing a lot of random input at security critical systems libraries, you can just throw random data and just check if it crashes. Because if it crashes, you know that's probably a problem. The problem is this doesn't work for models at all, because one thing about ML-enabled systems is that ML models very, very rarely crash. They basically always give you an answer. And that's a place where I think QA for machine learning is actually quite different than for regular software. And we'll see this in a bunch of places this semester, because it has implications for how we do QA over pipelines, for example. One thing that does work in regular software, and I think also in ML, not to spoil the ending, is using invariants as partial specifications. So for example, we might have this stack implementation, and we have a class invariant that checks before and after every method that the size invariant holds. That's always greater than 0, and it's always less than max size. Right? This doesn't prove that your implementation is correct, but it's a partial specification, and partial specifications are useful, I assert. Where was I? So what could invariants be in machine learned models, partial invariants? See, I was talking for long enough that you're like, thought you could check out. I know that happens. Yeah?
In a model that predicts on images, I could have it check the quality of the image, so the number of pixels in an image as like something for quality.
Well, so okay, if we're having a model look at an image, we might say that we could look at something about the quality of the image. So this would be maybe an invariant on the inputs to the model. We say, look, we don't expect the model to perform well on inputs of particularly low quality, right? By contrast, though, it's not necessarily an invariant on the output of the model, right? So if we want to think about an image recognition model, we might have partial specifications for what we expect based on something that we generated, right? Might be easier to think about NLP, actually, except at least because it directly relates a little bit to capabilities, right? We might have this partial specification that says, look, if we've inserted a negative, right, we expect the label to flip, right? That might be a partial specification. It won't always hold. But I think that the title being invariant here as opposed to partial invariant or partial specification may be a little bit misleading, because we want to think about things partially. I'm going to talk about a concept known as metamorphic testing, which is a concept from classical software engineering testing. But it might help us think about how to apply this idea to machine learning a bit more properly, right? The idea behind metamorphic testing is to exploit relationships between inputs. So the idea here is that if two inputs differ only in some number, then the output should be the same. If inputs differ by y, right, the output should be flipped. If inputs differ only in feature f, prediction for the input with the higher f should be higher. So here, we don't actually know what the correct answer is, but maybe we know that the answer should be the same or different based on properties of the input. So for example, if I have a model that is, I don't know, predicting whether somebody should receive an interview, I might say if the gender marker is different between these two inputs, then the answer should not change, right? It doesn't say that the answer needs to be that this resume leads to an interview and this resume does not. It says that whatever the answer is, it should be the same. And so this doesn't really require that you solve the Oracle problems. You don't need to know what the answer is, but you do need to think about how changes to the input would relate to differences in answers between two inputs. So sometimes capabilities can be expressed as invariants, and then can be encoded as transformations to existing test data in exactly this way that I'm talking about, right? So negation should flip sentiment analysis results, right? I have changed a feature of the input, and it means that it should be the opposite now. Doesn't mean that I know for sure that the sentiment for this one should be positive and this one should be negative, only that they should be opposites. So this helps you generate, right? Typos should not change the sentiment analysis result. Changes to locations or names shouldn't change sentiment analysis results. If I change JetBlue to Southwest, right? Proper names, then the sentiment analysis should stay the same. So here are lots of other examples, right? Credit rating should not depend on gender. And we can express these formulae by saying, look, if a model is a function between a vector description of the inputs, then if I change gender from male to female, the answer should be the same for all x. Right? Synonyms should not change the sentiment of text. Negation should swap meaning. Low credit scores should never get a loan. This one's a little bit different in the sense that it's actually saying what the output should be, right? Most of these are talking about how changes in inputs should or should not change the actual prediction result. This obviously requires domain knowledge, right? If we're thinking about a particular model. We're saying how relationships between the inputs and outputs shouldn't change, and there's a clear, I think, relationship between that and capabilities. But I don't think anyone in ML has ever used the word metamorphic testing, which is fine.
It's in a footnote in the capabilities paper.
Are they really? They're like HCI people, aren't they?
We cornered somebody at Dachstuhl and told them about metamorphic testing, and they put it in a footnote without any other context.
I mean, listen, metamorphic testing is one of those, like, I don't know, obscure corners of software engineering research in the 80s anyway. So the only reason we know about it is that we're huge nerds. But it is a useful concept. I think it's actually much more useful for ML than it is for real software in a lot of ways, for a bunch of reasons. So it's good it's coming back. You need to have knowledge of the domain. Good relations tend to focus on parts of the system or slices. Invariants are only covering one aspect of correctness. Sometimes invariants and near invariants can actually be mined automatically from sample data, or at least suggest them to you, and then you can use those to build upon. So there are a bunch of ways you can use invariants or check them, right? You can generate test data if you have them. You can transform existing test data. Adversarial learning can be useful here, so gradient-based techniques to search for invariant violations can be useful. I see a lot of this in testing of vision systems, trying to make very, very small changes to inputs using adversarial gradient stuff to come up with inputs that will lead to invariant violations. And it is roughly sort of morally analogous to symbolic execution in software engineering, which tries to pick inputs to drive program executions to particular corners to see if bad things happen, right? See if crashes happen. There is a little bit of work on formally verifying invariants for certain models. My sort of very high-level take on it is that, I don't know, it's not the way, but maybe Christian disagrees. Do you love that stuff, Christian? Me neither. Great. I can't always predict when he's going to love something secretly, but me too. So if I can summarize all the things I just said, right?
We're teaching it anyway.
Well, teaching is a super strong word. I was just like, it exists. It's kind of dumb. I don't really know if that counts as teaching it. If I can summarize, generating sample inputs is often easy. Knowing corresponding outputs is hard. That's true of both software and models. Crashing bugs are not common. You can use invariants in generated data to check capabilities or properties, which has a connection to the idea of metamorphic testing. If inputs can be computed from outputs, right, then tests can be automated. That's simulation-based testing that I might have slides on later. But first, let's talk about property-based testing. So far, all of my examples, right, expect some kind of ground truth output. But that's not true of a lot of models that we're talking about in 2026, right? Like, what about Gen AI, where there's no single ground truth available? I say, like, hey, like, Claude, generate a quiz for me. Create a well-crafted set of 4 concise answers for a test for a specific question. How would you test this? Like, hey, I give you this model. I tell you, hey, test this for me.
Maybe like benchmarks.
So maybe you have some benchmarks. I seeded that one, right, by saying, hey, like, if you look at some of the LLM benchmarks, they are basically doing capability-based testing. I didn't seed it on purpose, but I'm like, yeah, you might have some benchmarks that do this. How would you build that benchmark, though?
So I guess you would try to get like a bunch of like ground truth knowledge, or maybe like some sort of like human level comparison.
Okay, so maybe you want to get some quizzes from humans. Maybe you want to have humans make you some quizzes that are indicative. What else could you do?
But how do you know that what you're generating is any good? How close you get to the human one? Edit distance?
Sometimes.
Okay.
Right, so
Many possible quizzes, right?
Right, there are many quizzes. So the question is, how similar to your quiz does my quiz need to be?
Like, make an alpha product and make people rate the answers.
Okay, so maybe we just need to farm this out to Turk always. Okay. A human to judge it. This offers. There's trade-offs. Listen, it's engineering. There's trade-offs everywhere. So we have benchmarks, but we don't know how we're doing on the benchmarks. We have humans who we have to pay.
Use another model as a judge.
You use another model as a judge. I don't remember where the slides on that option are, but we can talk about it now. Oh, that was such a good throw. I'm very proud of myself. So what are the choices about using a model as a judge? Like, what are the trade-offs there? Is it a good idea or a bad idea? Well, I mean, yes, but...
I think it's a good idea. I mean, compared to using
Why?
human in the loop needs a lot more resources and time.
Okay, so the argument is that an LLM is fine and a lot cheaper than a human, so might as well. We will come back to some of the trade-offs, or at least ways to do this well, in a little bit. So I think you see at least a bit what some of the problems are here, right? Because the output, they're generating things. And so I actually, like, it's nice to have benchmarks, but like, and being fair to your answer, actually, about benchmark sets, like, I was talking about LLM-based systems, LLM-based benchmarks that are effectively doing capability-based testing, right? So if you think about human eval, which is the set of programming problems, same question comes up. How do you know you did a good job? Human eval does this by having a set of unit tests that are held out that says that evaluate the code that is generated. Okay, so you pass a human eval task if your code passes the test associated with the problem. Is this what is your opinion on this?
It's test, it could always like create code to return those specific values in the test.
Right, so there's always a person thinking adversarially. You've probably taken, your security person at heart, right? So the answer was, that was a terrible throw, I'm sorry. It was a good answer, it was a bad throw. So the answer was, one problem is like, look, you can just generate, if you know what the unit tests are, right? You say, well, okay, input 2, output 5. Input 3, output 7, right? You can write the adversarial program that is just, if input is 2, return 5. If input is 3, return 7. If input is 4, return 9, right? And that clearly is not really satisfying the prompt, which wants you to generally solve the programming problem. Which is to say that tests are a partial check of a specification, which is true. I will say that LLMs don't usually do that, which is kind of nice, but but tests are incredibly partial, actually. So like it is always, every system for automatic code manipulation or generation will at some point generate a program that passes the tests, even if they're held out, that does not generalize to what you actually wanted it to do. So you've heard of SweBench, which is one of these benchmarks for agentic issue resolution, like GitHub issue resolution. There the task is, here are some GitHub issues, and we want agents to resolve them automatically. We've determined automatically if they are resolved by running them on system tests that are not provided as part of the input system. And then, of course, all the follow-on papers that say, well, if you actually look at some of the pull requests that have been generated by agentic systems that pass tests, they're actually not great because the tests aren't fully capturing the specification, because tests never do. This is a problem in automatic program transformation that long predates the current boom of LLM-based systems. There's no perfect solution for it, but it does speak to this issue of how do you know that the solution is good, right? A lot of the times, at least in automatic bug repair kind of work, researchers have tended to use, is it, air quotes, roughly the same as a fix that the developer did for the same bug? Which is decent, but actually probably too strict. And also in the modern day, where everything's built on LLMs, you have the problem of data leakage, where like if it produces exactly the same thing a human did, like maybe it's because it actually saw the answer. I will give the ML community some credit, because when they first started applying things to code in, I don't say large quantities, they were using things like Blue and Code Blue, like standard NLP metrics, to evaluate the quality of the code that was produced. So that's basically a syntactic edit distance, right? The thing that Christian said, or that what we're using on quiz answer generation. The problem with that is that the difference between the code fragment return 0 and return 1 is only 1 character. And semantically, they're obviously extremely different. So, to their credit, they then reinvented the use of test cases as a metric for code quality, and claimed it as their own contribution, which good job, team. Academic siloing is amazing. And so it's much better than using NLP-based metrics, right? But it's still very partial. So it's actually a bit funny sort of to watch this evolution, because then for a couple of years, the AI NLP community was saying, oh, it passes the tests, it is correct. And then they were going to realize, well, okay, maybe not. So anyway, it's an ongoing conversation. And the point is that for generative AI, right, when the answer can vary from some established labeled ground truth, right, it can be difficult to know in an automated fashion whether the answer is good. Since having humans rate everything is kind of expensive, we have to do some other things. So property-based testing actually is one thing that is pretty reasonable here. Property-based testing, this is in the classic sense. Instead of writing unit tests, we know that we can test properties that a function should always satisfy. So if I want to test the greatest common divisor implementation, right, I'm going to assert things about the answer. I think that the answer should always be greater than 0. I think that D should always divide N, and that it should always divide M, right? And that no other number larger than D divides both N and M, right? This is expressing what the answer should be in terms of properties about the answer, not in terms of what the answer should be specifically. And if you can write this, then you can use this as a driver to generate lots of random inputs, right, and test it. And that's what property-based testing is supposed to do. I think it's a really cool idea. It hasn't taken off as much as I think it should as a cool idea. There are some really cool kind of frameworks for it. It came out of the Haskell community, of all things, in large part because writing these kinds of generators for more complicated data types is like super hard. And so it's actually harder to use for real software than it has any business being. I actually think it's almost a lot easier for models in some respects, right? So your goal is to create a well-crafted set of 4 concise answers. There should be only 4 answers. Every answer should contain less than 15 words. All answers should be covered in the course material provided as context. So if I can distinguish between capabilities and properties, right? Capabilities are what can the model do. Properties are what constraints should any output satisfy. And sometimes they're easier to express than others, right? But sometimes both apply. So getting back to LLMs as a judge, right? Because this was suggested. So I said, OK, we can give it to humans, but that's expensive. Is the answer relevant to the question, yes or no? This is tricky because you want to make sure that the LLM does align with human judgments. And like it often does, right? Like, because that's why LLMs are useful, but not always. One thing to do is to measure alignment between judge verdicts and human verdicts, at least on a sample. And even if it only agrees 70% of the time, right, it might be useful for catching regressions at large scale, right? Depends on what your domain is. The trick is to just be a little bit, careful, I guess. I will also say, although this is like a common practitioner issue of just assuming the LLM always agrees with humans, the academic nerd mistake is to forget that humans don't always agree with each other. So you're best off if you can at least know how often humans agree, because expecting the LLM to agree with the humans more often than humans agree with each other is maybe a little unreasonable. So the way you do this is that you provide, your prompt specifies your criteria, provides context, requests the verdict. Here are some common patterns, right? Does this response contain hallucinated facts, yes or no? Rate the helpfulness, right? Is a Likert scoring pairwise comparison? Which response is better, A or B? These are kind of standard patterns for this. It does actually work pretty well for a lot of domains. You want to think about cost versus latency and do an evaluation to compare to human criteria. But make sure that you may retain humans for particularly high-stake validation. So, breakout discussion number 2, because I managed my time. So let's write some property-based tests for this prompt. Right, I want to evaluate a system that does this. Your task is to analyze product handouts, summarize the handouts in a concise and clear manner, output your findings as a short memo I can send to my team. The goal of the memo is to ensure my team stays aligned on the project's objectives, timelines, and deliverables, while also identifying potential bottlenecks or challenges that could impact progress. Make sure to include all relevant details in your summary and analysis. So I want you to discuss property-based tests and what approaches you would take for executing them. Would they be programmatic? Would they be given to another LLM and so on? How would you express those inputs? How would you judge the outputs, et cetera? OK? Go nuts. And then we'll come back around. I would encourage you all to be a little bit more specific about how you're checking the property. So some of you are saying the property and saying, oh, give it this input. I'd also love to know how you're checking that the property holds, right? Like, are you writing code? Are you farming it to Turk? Like, what's the plan? All right, Christian, you don't have any candy. You have candy. We are hitting enter, and we are ready to tell us what properties are testing and how we're doing it. You guys are ridiculous. Just read what you wrote in the Slack. Like, read the words. You hit enter on words. Read them.
Hello. Okay, so it's like the pairwise comparison. And we use LLM-as-a-judge to do the task. And so based on, the prompt is kind of like based on those options. Please tell me which one do you think is better in some kind of dimension. You can list some situation or like what you are going to focus on. And please tell me the way, please list your own reasoning. Yeah.
OK, so I like that you're detailed about the method for using LLM as a judge. Can we dig down a little bit? What property are you testing? Right? What is the thing we want to hold that you're going to be using this to do? Because I can imagine one, if I can speak for you, right? So for example, maybe you could say that, I'm trying to think of one. Right. Well, is it concise? But you don't necessarily. But you don't need to do an LLM as a judge for is it concise, right? You just count words.
Take the next word. Is it clear?
Right, so you could do clarity, and maybe you could give it like 2 different ones that you force better reasoning by saying which one is clearer, right? And why, right? And that's a good one to use an LLM as a judge for, actually, because LLMs are pretty good at that kind of thing. Concise, I think, is easy enough. You don't even need an LLM for that, right? An LLM, you just count words. That's a Unix command. Anyone have something besides that? Either clarity, right, using an LLM as a judge, or concision, using WC-W. Yeah?
Invariants to be handout structure.
Invariant should be handout structure, so it should always have this structure. How are you going to check that?
So we can augment the data. We can jumble the sections of one handout and see if it's still generating the right kind of summary.
Right, so maybe the property is, okay, so we're almost there to an answer, right? The property is that it should always have these sections in this order. We might test it by taking some input data from our users and jumble it to make sure it always gives us the things in the right order. How are you checking that the sections are there and are in the right order? You've got some options.
You can, again, use an LLM to judge that.
We can use an LLM to judge. So it's funny, I've been working on sort of a toy AI-based system and vibing it really hard because I've been practicing my vibe coding. And I find myself when I'm vibe coding, like asking the LLM, like calling out to an LLM to do things that an LLM does not necessarily need to do. Like on this, I think you can like use some regular expressions, right? Like, and see where they show up in the document. I keep catching myself being like, wait, I don't need to use an LLM to extract this information. I can just get it from this spreadsheet. What am I doing? So I would encourage you to be careful that we're not making the LLMs do everything, because we're burning carbon for like literally no reason. You handed the microphone to someone to torture them. What would you like to say? I'm not trying to torture you. I'm just trying to make sure you're engaged.
Yeah, we try to test the milestone temporal integrity.
Okay.
Yeah, we like to examine the timeline in the memo.
Okay.
And it should be consistent with the source document, and the milestone date in the memo should exist that was not present in handouts.
Okay, so there's a...
Be preserved.
Okay. Keep going.
And so our test method will be extracting all dates and associated events from both the handout and the memo, and use a script to verify that the memo milestones is a subset of the handout milestones, and the relative order remains unchanged.
Right, so this is string manipulation in Python you're proposing. I'm going to do an extraction. I'm going to look for things that look like dates. I'm going to make sure that all those dates also appear in the produced memo, and I'm going to make sure they show up in the same order, right? Maybe there aren't extra dates. I don't actually know if this is more or less robust. I think it's decent compared to using an LLM as a judge, but I like it for not always relying on an LLM because it's kind of an easy answer. And sometimes you really don't have to. Sometimes you don't have to. All right, I'm going to talk about one more thing and then let you go, unless Christian wants to add anything on property testing in LLMs.
I was just running out of chocolate.
You're just running out of chocolate? Okay. That's just too bad. The last testing concept I want to touch on before we go, because it is 3:16, a little bit of a grab bag. There's a bunch of slides at the end that's like, other stuff from testing, and I don't want to go through the grab bag. I'm just going to talk about simulation-based testing real quick, because there are a lot of cases where it's actually quite easy to go from outputs to inputs. So here's an example from primes, right? You can generate primes and then use that to test a thing that factors primes. Especially in vision systems, you can derive input-output pairs from simulation. So this is very common in self-driving cars, right? Where, for example, you might render a scene and add certain kinds of noise, and then compare results with the simulator state, right? This is very common in especially like vision-based or graphics-based system. Qualities can depend on the quality of the simulator, but not necessarily in the way that you think. And one thing that self-driving car researchers get frustrated about is simulation companies focusing on ever higher quality fidelity when actually you don't necessarily need maximum quality fidelity. You just need fidelity along certain axes that are particularly important. So even though quality does matter, it's not necessarily it's kind of a nuanced conception of quality, is what I'm trying to say. It's not going to work as well for things where the input-output relationship is not as well known. So things like cancer prognosis or housing price prediction. It's not very useful for that. But in autonomous driving, simulation-based testing is extremely common. And that was the last grab bag thing I wanted to do. I'm not going to cover coverage and stuff like that because, well, maybe I'll talk about continuous integration. Continuous integration is now sort of bog standard for, testing continuously deployed software, where when changes are pushed to the code base, they are automatically integrated into the code base and tested. It is worth thinking about doing this. We will be talking about quality assurance in sort of a pipeline sense in much more detail later in the semester. So this is like sort of prefacing some of that. But it is worth thinking about continuous integration for model quality. So having a testing script that does things like automatically evaluate models on a training set, reporting accuracy, deploying learning and evaluation tests, cloud services, and fail tests below certain accuracy bounds, and making sure that you're versioning test data, and having your continuous integration trigger things, parsing outputs, plotting for comparison, especially for continuously trained or checkpointed models, is very helpful. We will be talking about all this, but the point is just to whet your appetite for it because it's going to come back. So what did I talk about? I talked about curating test data by analyzing specifications. We often use the word capabilities for models. You want to identify important inputs and slice data and use that to generate relevant tests. I also talked about ways that we can do some automated testing, or at least in cases where we can maybe generate inputs but don't have outputs. And this, I think, is becoming actually a lot more pertinent as more of our systems move into the generative context and away from kind of the traditional labeled input-output data. So thinking more about how to use LLMs as a judge or how to express properties of good outputs from Gen AI kind of contexts, I think will be increasingly important. And on that note, it is 3:20. So I invite you to enjoy the rest of your Wednesday afternoon, and we will see you Monday.